So welcome everybody to the One World Mathematical Game Theory Seminar. It's our first seminar for this academic year. And we're happy and proud to have here with us today, Yakov Babichenko from the Technion. He's quite a versatile researcher. He does adaptive learning in games, complexity of equilibria, aggregation of information, and lots more. And today, he will tell us about a population's feasible posterior beliefs. This is joint work with Itai Arieli. And the stage is yours.
Thank you, Galit. Thank you very much for inviting me, for having me. So this is a joint work with Itai Arieli, and it focuses on quite a simple setting. The setting are as follows. We have n Bayesian agents who share a common prior mu and are exposed to some private information about an unknown state omega. Namely, they not necessarily observe the same information, which may observe different information. And the question is, which distributions of posteriors can the agents have? Okay, so this is just let me clarify what I mean by that. So let's focus on the simple case of binary states. Then an information structure is essentially a correlated distribution between states and signals. For example, this distribution. But in many practical situations, we don't really care exactly about the information structure. What we care about is about the distribution of posterior that it induces. In particular, if the agent observes signal S1, his posterior will be 2/3. It's 0.2 divided by this sum. Okay, and the probability for this posterior will be 0.3, which is the sum of these two probabilities. Okay, and we have 1/3 with probability 0.3 and 1/4 with probability 0.4. Okay, so this is a single agent case. So for a single agent, a distribution of posteriors, we say it's feasible if there exists an information structure with prior mu that implements. Okay, mu is the prior. And the characterization of the set of feasible distribution of posteriors is very elegant. It's a classical result, sometimes called the splitting lemma of Aumann and Maschler. In fact, a similar version appeared already in the seminal paper of Blackwell on experiments. So a distribution is feasible if and only if its expectation equals the prior. Okay. So we have a complete, very nice answer for this question for a single agent. But what happens if we have more than one agent? For instance, let's focus. Yes?
Do you only have two states, or is it? Can this be generalized?
The splitting lemma holds for arbitrary state space, but for a single agent.
But
okay,
But 0, 1 is the only two states, right? I mean, the interval 0, 1, or do I misinterpret that?
Yeah, but the splitting lemma is correct for an arbitrary state space, let's say for an arbitrary finite state space. But then it's a vector, and you want that the expectation of this vector will be equal to the vector of the prior. So what about more than one agent? So let's stick to the case of binary state space for now. So the expectation condition is obviously necessary. Why? Because if we think of one agent, then his posteriors should be feasible, and also the same thing for the other one. So it's definitely a necessary condition, but it is insufficient for feasibility. Consider, for instance, the following distribution. So now we are talking about pairs of posteriors, which are points in the 0, 1 square. We talk about distributions over this square, and consider the distribution that assigns a probability of 1/2 to the point 0,1, namely with probability 1/2, the first agent has a posterior of 0 and the second agent has a posterior of 1. And with probability 1/2, it's the other way around. Player 1 has agent 1 has a posterior of 1 and agent 2 has a posterior of 0. This distribution satisfies the expectation condition. The expectations are fine, but it's obviously is infeasible. How I know that it's infeasible? If you have, it cannot be the case for Bayesian agents that one will be certain with positive probability that one will be certain that the state is 0 and the other one will certain that the state is 1. In fact, you have no distribution with positive atom on these 2 points in any feasible distribution. Okay, so this is an infeasible distribution which satisfies the expectation condition. Okay, and the question is, what is a necessary and sufficient condition for feasibility? So this question, specifically for the case of, sorry, was there a question?
Yeah, if I may, could you please repeat why that is an infeasible distribution, the one on the previous slide?
Yeah. Okay, so this distribution is infeasible because it puts a positive weight on the event that player 1 will have a posterior of 0, while the other will have a posterior of 1. Okay, if you have a Bayesian agent that believes that the state is 1 with probability 1, then since he's Bayesian, the state must be 1. And it cannot be the case that the other one will assign a probability 0 to this. Okay?
Thanks.
So, Yakov,
yeah.
So if you replace 0, 1 with epsilon 1 minus epsilon, and similarly 1 minus epsilon epsilon for the other, that would become feasible?
No. So in this specific example, let's just do this exercise, for instance. Let's replace it by 3/4 quarter and 1/4 3/4. I claim that it's again infeasible. And the reason for that is from a different reason, which I don't want to go deeply into it, but essentially you can think of it as the Aumann agreement theorem, right? What does it mean that you have a distribution that which has the element 1/4 3/4, but doesn't have anything else for player for player 1 on his axis and has nothing else for the other player. It means that the players agree to disagree. Player 1 knows that the posterior of his opponent is 3/4, while he holds a posterior of 1/4, and this is another reason why this is another example which is slightly more complicated to explain for an infeasible distribution with correct expectations. Okay, so here is a necessary and sufficient condition which has been developed by de Groot, David, de Groot, Morata, et al. It says the following: take a distribution and take any 2 subsets of the 0,1 segment. Then the probability that the measure P should assign to this rectangle, which is A and B complement, should be greater or equal than some conditional expectation minus some. So essentially, you have this inequality, and I don't want to go too deeply into these inequalities. This is not really the topic of this talk, but I can tell you that these inequalities has a very nice interpretation in the context of agreement theorem. It can be viewed as some version of approximate agreement theorem, and also a very nice interpretation in the context of no trade theorem. You can think of it as as a statement that says that you cannot in a common knowledge, common value setting, you cannot have some arbitrage. That someone will gain money from the sky. Okay, so these interpretations appear in the previous paper of Itai Arieli, Fedor Sandomirsky, Omer Fanuz, and myself. But note that this elegant characterization. It's not very simple in the sense that it requires us to search over subsets. We need this inequality to hold for all possible subsets. So, for instance, if you have a distribution with support n, then you should go over 2 to the power n subsets, and it has extensions to more than 2 agents and to state spaces that are non-binary. It appears in the paper by Morris and also in our paper. But those extensions are somewhat complex in the sense that they are in fact even more complex than this characterization, because there we need search over functions rather than subsets. So you can think of subsets as indicator functions, and over there indicator functions are insufficient to characterize. You need to go over some functions. Okay, so this is what is known essentially about this question of feasibility. And today I want to discuss some anonymous variant of the feasibility question. And in a moment, I hope it will become clearer what exactly what I mean by anonymous variant. So let's take an example. Let's consider the binary state space case. And let's the prior to be uniform with 1/2. And you have n agents, let's say many agents, and here is an assumption. The assumption says that no matter to which information an agent is exposed to, his posterior will either be 1/4 or 3/4. Okay, it always will be either 1/4 or 3/4 with probability 1. And this is why I call it an example, because later we'll drop this example. This assumption. So when agents are exposed to their information, to the signals, S1 to Sn, then it induces, every agent will have either a posterior of 1/4 or 3/4, and I denote by F the fraction of agents with the high posterior of 3/4. This is a number between 0 and n, or it is more convenient to me to think of it as a fraction. Okay, so this is an element in a discrete. Okay, and so since every signal realization induces such a number, then the information structure, which randomizes this S1 to Sn, induces a distribution over these fractions. And so P is a distribution of posteriors in the population. And the distribution over posteriors in the population. And note the distinction of this object from the one that we discussed before. Before that, I really wanted to say which agent holds which posterior, so it was a distribution over this set of 1/4, 3/4 to the. And now I only care about which fraction of agents hold posterior, and this is a simpler element that it's only a distribution over n+1 elements. And the question, which distributions over this 0, 1 over n to 1, which distributions are feasible? And here is the answer to this question. A distribution P is feasible if and only if it is a mean preserving spread of the distribution with two atoms, one atom at the point 1/4 and one atom at the point 3/4. So essentially mean preserving spread means that you split this 1/4 to some points of this grid, such that the expectations will be 1/4. You split these points somehow on the grid such that the expectation will be 3/4, and essentially the combination of these two splits is the mean preserving spread. Okay, so this is the answer to the question which distributions are feasible. Maybe it's a good point to notice that if you are somewhat familiar with questions that related to information, then many times the notion of mean preserving contractions and mean preserving spread play a central role there. And it's a different way to think of information in some cases. Here, I want to notice that it's somewhat different because the spreads and the contractions in the other contexts of information typically are done in the space of beliefs. Here, it's not in the space of beliefs. This is in the space of frequencies of agents with some belief. Okay, so it's in a different space. It's mean preserving spread in a different space. Okay, let me let me convince you why indeed this is the answer to the question. Okay, so let's solve this example. So just another way to write the fact that P is a mean preserving spread of 1/4 of this distribution is to say that there exist two distributions, one with expectation 1/4, the other with expectation 3/4, such that P equals to the context combination of them with probabilities half-half. Okay, so we should show two things. First of all, we want to say that if a distribution is feasible, then necessarily P is an mean preserving spread. Okay, so how we do that? There is a very straightforward argument. Conditional on the low state, every agent has the posterior 3/4 with probability exactly 1/4. Okay, this is true just because this agent is Bayesian. Okay, so he must have this posterior with probability exactly 1/4. Therefore, conditional on state omega equals 0, the expected frequency of agents with posterior 3/4 is 1/4. This is just by linearity of expectation. Sorry.
I'm curious. So I guess I've missed something. Why is the conditional on the low state? Why is the posterior of every agent 3/4 with probability 1/4? Why is it with probability 1/4?
Okay, so this follows from the fact that the agent has just two posteriors, 3/4 and 1/4. Okay, and the ex ante, these probabilities must happen with probability 1/2 because the prior is 1/2. Okay, and from here you can, from the ex ante distribution of posteriors, you can there is a simple formula to calculate from the ex post probabilities conditional on each and every step. I didn't write the formula here, but essentially this is just simple algebra, somewhat playing with the inequalities, but linear qualities, and there is a unique solution for that. And from here you can deduce these probabilities.
Okay.
Okay, so just the issue to remember here is that for a single agent, given an ex ante distribution of posteriors, one can deduce the distributions conditional on a state for every state. And this is true not only for two binary states. In fact, it's true for any number of states. And there is a simple formula for that. In the case of 3/4, 1/4, it is exactly 3/4, 1/4. Another simple explanation for that is you can think of this information structure as a coin that reveals that shows the correct state with probability 3/4. Okay, so what is in the low state? What is the probability that the agent will observe the wrong state? It's exactly 1/4. Okay, so so conditional on state omega equals 0, the expected frequency of agents with posterior 3/4 is 1/4. And here note that we use the fact that we don't know what is the correlation between the posteriors, but we don't really care for expectation. We don't really care about that. And this is the P0 is exactly the distribution with expectation 1/4 in the mean preserving spread. And similarly, you define P1 to be the distribution conditional on state 1, and this one must have an expectation of 3/4. And this completes the first direction of the exercise. We show that every distribution that is feasible must be a mean preserving spread. What about the opposite direction? So for the opposite direction, we should design an information structure such that we are given P0 and P1, and we want to design an information structure such that the distribution of frequencies of posteriors will be exactly as we have P0 plus half. Okay. So how we do that? So conditional on state 0, what we do is we choose a random subset of agent of which size. The size of the subset will be drawn according to this distribution P0. And to all these agents, we will send a high signal. Okay. What we do at state 1, we choose a random subset of agents of size of a random size. The first, so when I say random subset, I mean uniformly at random among all subsets of this size. And the other one is not uniform; it's by P0 or P1. And we send to all these agents again the high signal. Now all that remains is to do some simple calculations that to see, given that an agent observes a signal age, what is the probability, or what is his posterior? And it turns out that his posterior turns out to be precisely 3/4. Okay, and you can do the same with the low signal, right? If you didn't receive a high signal, means that you received the low signal, and to see that in this case the posterior is 1/4. Okay. So this completes the exercise, and if you notice, essentially, these to solve the exercise, we didn't use some complicated duality theorems or something. It was just simple calculations so far. And the nice thing about simple calculations is that sometimes they naturally extend to more general settings. And in fact, this is exactly the case here. So far, we looked at the case of binary state space and the binary signals for each agent. And here is the general case. So let's understand which object are we looking at. So we are given a distribution P that is in delta of delta of delta of omega. So the inner delta of omega is a posterior of an agent. This delta refers to the fact that distribution, this is where we are considering distribution of posteriors in the population, okay? And the first delta is the randomness of the signals that induces the randomness on the distribution of posteriors in the population. Okay, so this is the object that we are looking at. And here is the theorem. A distribution P is feasible if and only if, and then omega can be an arbitrary state space, arbitrary finite state space, not necessarily binary. If and only if P is a mean preserving spread of this convex combination of distributions. So what is this convex combination of distributions? It assigns a probability that according to the prior. This is why in the previous case you had 1/2 something plus 1/2 something, and to which distribution it assigns it? To the distribution P hat of omega, so P over line omega. So what is P over line omega? To understand that, let's first understand what is P over line. P over line is a simple object. It's just the expectation of P. Let's interpret the notion of expectation of P in somewhat in a different language. So essentially, P over line is the average frequencies of posteriors. I'm taking each and every possible posterior, and I'm asking how frequent it is overall. Overall, I mean, when I ignore this randomness of signals, I'm just taking the expectation. Okay, and now, as I mentioned before, there is a simple, clean formula for calculating the X. And now I'm thinking of P hat as if it was an information structure of a single agent. It is not. It's a somewhat average frequencies of posteriors, but I think of it as if it was an information structure of a single agent. And for a single agent, single hypothetical agent, or you can think of him as single average agent. And for this agent, we can deduce from P over line the conditional distributions over posteriors, conditional on each and every state. Okay, so this is where P hat omega is the conditional frequencies of posteriors for an agent that is induced from P over line. Okay, so and as I said, the simple formula for that. Okay, so this is the theorem. It provides us a necessary and sufficient condition for feasibility in an anonymous setting, right? It's not in the standard. It's not in the previous setting where we cared about which agent hold which belief. Here we only ask in average in the population how many agents will have this posterior and how many agents will have this posterior, and so in some sense, it's kind of an anonymous version of the feasibility question.
Question?
Yeah.
So the anonymity is just in the word, I mean, in the notion of mean preserving spread, or is it also in the notion above with the triple deltas?
So the anonymity here is in the question that we posed. The feasibility question that I started with considered, let's say, two agents, and then we knew the first coordinate was the posterior of agent 1, and the second coordinate was the posterior of agent 2. And we really, in the formulation of the problem, we knew to distinguish who holds which posterior. If you want to take the same example with two agents, then the elements that you will have is, let's say, you might have a situation where it is told to you that one agent, I don't tell you who this agent is, one agent has a posterior 3/4, and one agent has a posterior of 1/4. But I'm not telling you this is agent 1 has a posterior of 3/4 and agent 2 has a posterior of 1/4.
Okay,
so the question that we pose is in a different state space. Here we consider delta of delta of delta of omega, and if you want the analog of this question for many agents, it will be just delta of delta to the power omega to the power n.
I see. Mm-hmm. Okay, thank you.
So this is the distinction. Okay, so let's say what is nice and what is less nice about this theorem. So as I told you before, the nice thing about this theorem is that the complexity of the characterization does not increase with the number of agents. In fact, if you look at the theorem, you don't even find here the notion, the letter n. So let's fix it. It should appear, but let's understand where it plays a role. It plays a very minor role. So we don't, the elements that we are talking about, right? If we have a population of 7 agents, then it can never be the case that 1/4 of the population will have some posterior. Okay, it must be the case that it's either 2/7 or 3/7 or something. Yeah, so if I denote by delta n to be the frequencies, the consistent frequencies that can appear, so essentially it's only, this is the only place where the number of agents plays a role. Okay, the distribution obviously has the correct frequencies. So this is the only place. And this is in contrast to the other feasibility question, where the number of agents really complicate the problem, even when we jump from 2 to 3. Another thing to point out is that it doesn't really increase, the complexity doesn't really increase with the number of states. I mean, instead of having here a mean preserving spread of a distribution with 2 atoms, we maybe have a distribution with 3 atoms. Okay, it's not really much more complicated. But let me also point out some disadvantage in some sense, but because not everything is so simple, is that the characterization increases, the complexity increases with the number of possible posteriors. Where can I see that? So if the elements that we are talking about here we have many possible posteriors, then this distribution will be in a high dimensional state space, and the mean preserving spreads itself in high dimensions is quite complicated object. Okay, so if we have let's say 3 posteriors instead of 2, it's slightly more complicated, because then we should talk about, instead of 1-dimensional mean preserving spreads, we should talk about 2-dimensional mean preserving spreads, which is more complicated object. Okay, but somehow probably unavoidable, because the feasibility question itself is not very simple. Nevertheless, I want to show you, what I want to do next is to show you applications of this theorem. How can we use it to solve some problems? So one application that I want to show you is in the context of polarization. Okay. By the way, maybe questions so far? Okay. So one application is in the context of polarization. Generally speaking, the question that I want to pose is how polarized can the posteriors of Bayesian agents be? Okay, they are exposed to some private information, and how different their posteriors can be. Let's focus on the simple case of just 2 agents and the binary state space. Okay, so here is a possible measure of polarization. You can take, now we go back to the case of X1, which denotes the posterior of agent 1, and X2, which denotes the posterior of agent 2. And we can ask what is the distance to the power alpha, and what is the expectation of the distance of their posteriors to the power alpha. Okay, and I want to understand how large can this object be. Obviously, for instance, if we send them public signals, they both observe the same thing, then the polarization, according to this definition, is zero. You always can have polarization, but can it be large? Okay. So this question has been studied previously. Maybe the first paper was by Dubins and Pittman in the 80s, and Budzi and Pal, and also we have some results about this question. But maybe it looks very simple, but it turns out not to be such a simple question. Let me tell you what is known. So from all these results, essentially, the bottom line is that if the power alpha is smaller or equal to, then the maximal polarization is obtained by fully informing one agent and no information to the other. For instance, in the case of a prior 1/2, it means that one agent will constantly has the posterior of 1/2, and the other one will either has a posterior of 0 or of 1. And in this, for instance, for alpha equals 2, you can constantly have a polarization of 1/4. Okay, so you can easily achieve 1/4, but it's really not easy to prove that there is nothing better to do. Okay, the proofs are not one-line proofs. It's more kind of two-page proofs for these results. We don't know of a simple proof for that. Just to show you that those are quite complicated questions. So for alpha greater than 2, it's an open problem. What is the minimal polarization? All I know to say is that full information, no information is no longer the one that maximizes polarization. I know to beat the full information, no information, but I don't know to prove something that something is optimal there. Okay. And just to say that for more than 2 agents or more than 2 states, nothing was known. And what I want to show you now is exactly something about more than 2 agents and more than 2, and also more than 2 states.
Could you perhaps give some intuition why 2 is such a threshold?
I can.
If there exists,
I don't know if I can tell you precisely why 2 is the threshold, but I can give intuition why for large. If you think of alpha as very large, why full information, no information is not a very good idea for you to maximize polarization. This I can do.
Why?
Let's give the intuition for that. So think of alpha is very large. Then the policy that I just described of full information, no information, it gives you constantly 1/2 to the power alpha, which is quite low number. Okay, how can I do something better than that? I can send to both agents, for instance, an information that puts their posterior somewhere, let's say, at the point 1/alpha and 1 - 1/alpha, namely almost to reveal them the entire information. Okay, then in the rare event, but yet not very rare, when they have these two extreme posterior, they disagree. In this case, they disagree. Their disagreement is very close to 1. And when you take it to the power alpha, you essentially get something that is constant and not something that is exponentially small. So, and the
How can
probability
you
of
make
such an
the
event
posterior
is,
be such far away? How can you, do you have an intuition how you can actually cause the posteriors to be in such a distance? What?
exactly. So for instance, if you send them conditionally independent signals, okay, if you send them conditionally independent signals, then there is this event where one gets the correct then essentially it requires some calculations. But what I want to say is that with probability of approximately of order 1/alpha, this event of having two very far posteriors, not with probability close to 1, not even close to 10, with probability just 1/alpha, they will have such a posteriors.
But then it's if alpha is large, then 1/alpha is small.
Exactly, but it's much better than 1/2 to the power alpha, which was the previous one.
Okay.
Yeah, so I agree. It's still something that happens just with probability 1/alpha, but it's better than 1/2 to the power alpha.
Okay.
Yeah. Okay, so what I want to do now is to tell you something about more than the polarization with many agents. So first, let me suggest you a measure for polarization. The measure that I want to suggest is quite simple, is the variance. The variance of what? The variance of the distribution of of posteriors in the population. Okay, so if you have a frequency of 1/3 of agents with posterior 0.1, 1/3 of agents with 1/2, and 1/3 with 0.6, I can think of it as a distribution that gets just 3 values, which are the posteriors, and I'm looking at the variance of this distribution. Why it's kind of a reasonable measure to consider. So here is one explanation that in the case of 2 agents, this measure exactly coincides with the alpha equals 2 case, right? Essentially, if you think of distribution that gets 2 values, x1 and x2 with probability 1/2, then its variance is x1 minus x2 squared multiplied by some constant, which in this case is 1/4. Okay, so this is therefore it's essentially the same question as alpha equals 2. Okay, so this is the measure that I want to suggest, and here is a proposition. For every population of even size, if the number of agents is even, the maximal polarization is obtained by full information to half of the agents and no information to the other half. Okay, so it extends the result for the case of 2 agents. It tells you, and obviously from here it's also very simple to calculate the exact number of what is the optimal, what is the maximal polarization. Okay, so this is the result. Let me notice that it naturally extends also to state spaces that are non-binary. If you define again the polarization by a variance, then essentially the proposition remains the same. Let me give you the proof idea of this result and how it utilizes the characterization that I just showed you. So by the theorem the main theorem, we know that the distribution P is a mean preserving spread of 2 distributions, P hat 0 and P hat 1 with weights 1 minus 2 and 2. And now I want to consider another distribution over frequencies of posteriors So before that, we start with this distribution that splits the weight on P0, and we have another distribution that splits the weight on P1. And I want to consider another distribution that instead of splitting it, that it deterministically equals to the spread of it. Okay, instead of splitting it, I'm deterministically assigning it to be this distribution. Okay, so just to clarify, let's say that from the point 1/4, I spread it to 0.2 and 0.3. Instead of it, I consider a situation where the population of agent is deterministically, half of them are at 0.2 and half of them are at 0.3. Okay, this is what I mean by that. And notice that this might require an infinite population of agents. It's why? Because frequencies must, we said that they must have the correct denominator, and no one told us that P0 has the correct denominator. Okay, so let's look at this notion of the variance. So it turns out that by this deterministic switch from spreads to deterministic distributions, the expectation of x squared remains unchanged, because essentially it gets the same number with the same probability. X gets the same number with the same probabilities, and therefore it does not change. What about the expectation of x to the square? This, because x squared is a convex function, then by doing this deterministically, it decreases. Okay, so overall, we found that that such a change of distribution to a deterministic one, it reduces the variance. So it essentially reduces the problem to one with deterministic distributions of posteriors conditional on state. And all that remains is some simple calculations that to optimize now over deterministic distributions over posterior. All the complicated part is to try to be avoid of these spreads. And this is something that we were able to do using this argument. And I will not show you these calculations, but essentially just some integrals and not too complicated. This completes the proposition. Just to let me raise an open question. What happens for, let's say, 3 agents? Okay, so the theorem says that for every even number of agents, full information, no information is optimal. I don't know the answer to this question. I don't know what is the maximal polarization, but I know to tell you that the full information, no information is no longer maximizes polarization. Here is an example of information structure. This is essentially the distribution of signals for agents 1 and 2, and the state is fully revealed to the third agent. So you can see that essentially agent 1 and 2 will always have either posterior of 1/3 or 2/3 in this information structure, and it turns out to beat the full information, no information one. And the conjecture, just because we played with these matrices a lot and didn't find anything better, a crazy conjecture, I don't know, that this one that I showed you here is the optimal one. Okay, we have some reasons to believe that it's correct, but yeah. Okay, so this is the conjecture. Finally, I want to show you another application. It will be also very fast. Another application in the context of private Bayesian persuasion. Okay, so I want to think of a situation where we have sender. So we have a binary state space. You have the agents share a common prior view about the state, and the sender communicates privately with n receivers. Okay, he can send each agent a message that only this agent will observe. Okay, each receiver, after learning something about the state, he has a binary action. Let's call these actions either 0 or 1. And let's say you can design the utilities of the receiver such that receiver I will take action 1 if and only if her posterior is weakly above tau. Okay, tau is some threshold. Above this posterior, the agent takes action 1. Below it, it takes action 0. What about the sender? So the sender, I want to consider somewhat, again, an anonymous version, an anonymous variant of a Bayesian persuasion problem, where the sender doesn't really care about the exact which agent took which action, but he cares only about the fraction of agents who took action 1. Okay, and let's say that U of F is where F is, and just for simplicity, let's assume that it's also state independent, but the result remains true also for state dependent utilities as far as they are anonymous of the sender. Okay, so U of F is sender's anonymous utility, and let's think of U as monotonic, namely he prefers as many players as possible to take action 1. Okay, and this is why it's yeah. So U is monotonically increasing. What was known about this problem? So in a joint paper with Itai, we consider the case where U is a supermajority, namely it's a step function. It jumps from 0 to 1 at some threshold. And we also consider the case where U is a concave function. In these two cases, we knew nice characterization. And now let me show you that this problem can be also solved with our theorem for an arbitrary monotonic utility. So I want to define a notion of concavification on a grid. So if you have some function, I don't really care about the entire function. I care only about what happens on the grid. I'm looking only at the black points, and now I'm taking the concavification of these black points. Okay, so it's the same notion of concavification, but you now restrict yourself to distribution, not only with the correct expectation, but also with the correct support. The support must be a subset of this grid. Okay. So this is the notion of cav NU, not cav U. Cav is the concavification. Cav N indicates that you do concavification over a grid. And here is the proposition. For every monotonic U, sender's optimal utility is this some formula, essentially that what it does concavification to the function U. By the way, this picture is not very good because the function U here is not monotonic. So it does a concavification and it evaluates it at some point. Okay, so it's quite simple expression. Let me again tell you about the distinction of this expression from the standard concavification classical characterization of Aumann and Maschler and limits against, etc. So what's the difference? Over there, again, the concavification is done in the space of posteriors. Here we are talking about the space of frequencies. Okay, so this is the difference. The concavification is on the space of frequencies of posteriors. And this expression is exactly mu, I recall, is the prior and tau is the threshold. So this expression exactly captures the frequencies in some case. So let me give you a key idea of the proof. and also to interpret this expression. So the key observation, which is not hard to deduce, is that in the case it is optimal for the sender always to induce either a posterior of 0 or a posterior of tau on each of the receivers. Okay, he doesn't, in the case of tau, he will take action 1, and in the case of 0, he will take action 0. And he doesn't want to spend more kind of weight to increase his posterior above tau or above 0. Okay, so this is the key observation. And once we have this observation, then we can utilize our characterization, because we know that every agent will have only binary posteriors. Everyone will either have a posterior of 0 or a posterior of tau. And essentially, this is all the idea. And now you should only translate posteriors to frequencies of each posterior in each state. So for these two posteriors, it turns out that at state 1, all the agents has the posterior tau. All the agents have the high posterior. And at state 0, doing this calculation lead you exactly to the fact that at state 0, this expression is the frequency of agents with the high posterior. And what is the flexibility of the sender? As our theorem states, it essentially allows you to spread this point to any point on this grid, and this is why we get exactly Kav and U at this point. Okay, and I think.
Can I have a question?
Sure, sure.
Pamela, can you explain in the case where mu is equal to tau to 1/2, what gives the formula?
Again.
In the particular case where mu is equal to tau, so you want in state 0 that everyone will take action 1?
Yeah, in this case, I think if mu equals tau, then and both equal 1/2.
Yes, for instance, yes.
In this case, it gives you 1, right?
Yeah, you can have you can have 1 always.
Yes, because the threshold is 1/2 and the prior is 1/2. So, for instance, by not revealing
you send no information,
they all will take the action, the action that you want, which is the action 1.
Okay, thank you.
Okay.
Thank you.
Thank you.
Thank you. Now we begin the less formal discussion. Questions, people, if you have any, please unmute yourselves and ask. Okay. Okay. So thank you again.
Thank you.
Thank you. Thank you very much. I stopped the recording.
Bye.